A telescope, still warm from a craftsman's hands, glinted under the flickering lamplight in a London attic. Through its lens, the night bloomed with a startling complexity. The stars, once eternal fixtures of divine narrative, now shimmered as unresolved questions. When William Herschel trained his eye through that lens, he saw not just stars, but whole systems whose very light had begun its journey before human history had written its first verse. At that moment, something ancient unraveled. The cosmos was no longer a painted dome, but a sea of structures, unbounded in their number and their scale. And yet, for all its poetic allure, astronomy after Newton moved slowly. The laws of motion and gravity had been declared, but the instruments needed to test their implications across the heavens were still crude. Telescopes lacked precision. The photographic plate and the spectroscope tools that would later revolutionize how we decipher the light of stars had yet to be applied to the sky. The 18th and 19th centuries were marked not by the rapid conquest of the stars, but by a long, methodical awakening. Beneath those incremental advances lay the stirring of deeper questions. What were the nebulous smudges in the night sky? Were they clouds of gas, unresolved clusters of stars, or perhaps entire galaxies too distant for even the sharpest eye? The distinction was not semantic. Embedded in it was the tension between two worldviews, one that imagined a single galactic system, an island cosmos, and another that dared to envision an endless archipelago of galaxies scattered through infinite space. Thomas Wright of Durham, in his 1750 book, An Original Theory of the Universe, proposed that the Milky Way was not a chance scattering of stars, but a structured entity. He imagined it as a ring or spherical shell of stars, with a divine center, a kind of gravitational sanctuary of cosmic grace. Wright went further, speculating that the nebulae seen faintly through telescopes were other Milky Ways, other creations spinning in the depths. His ideas struck a chord with a young Immanuel Kant, who absorbed Wright's vision and re-articulated it in more rigorous, secular terms. Kant described the Milky Way as a rotating disk of stars, bound by gravity, and posited that the hazy patches of light across the sky were analogous systems galaxies. He imagined a grand hierarchy, stars clustering into galaxies, galaxies into clusters, clusters into superclusters. It was an intuition that prefigured our modern understanding of large-scale structure. But to Kant, it was more than structure, it was metaphysics. Infinity, for him, was not merely unending space, but the exhaustion of the imagination itself. As telescopes improved, these early metaphysical musings began to confront empirical resistance. Astronomers like William Herschel turned observation into cataloging. He and his sister Caroline charted thousands of stars and nebulae, peering deeper than anyone before. At first, they assumed that all stars were suns like our own, evenly distributed, and that dimmer stars were simply more distant. These assumptions shaped a model in which the Milky Way was a flattened disk with the sun near its center. But one by one, those assumptions failed. Obscuring clouds of interstellar dust masked vast regions of the galaxy. Star brightness varied immensely, and space was anything but uniformly populated. Herschel's belief that starless regions were holes in the sky, windows into the void, was, in retrospect, an early misunderstanding of cosmic dust. But his intuition that nebulae might be island universes similar to the Milky Way proved prescient. Over time, even Herschel grew skeptical of his initial certainty. Some nebulae, he noticed, looked like glowing fluids rather than star clusters. Others remained obstinately unresolved even under the best telescopes. Still, the dominant view in the 19th century, especially in Victorian cosmology, was conservative. Agnes Clerk, a respected chronicler of astronomy, wrote in 1890 that no competent thinker could suppose a nebula to be a separate star system. The galaxy, our galaxy, was the universe. Beyond it lay darkness, mystery, or perhaps the throne of God. This was the culmination of a one-island vision, steeped in the old Stoic model but now dressed in atomic theory and Newtonian mechanics. And yet, cracks in the Victorian universe had begun to form. Spectroscopy, the science of dissecting light, was making the heavens chemically knowable. William Huggins, aided by his wife Margaret, used this tool to compare starlight with elements tested in laboratories on Earth. When he aimed his spectroscope at a planetary nebula in Draco and saw not a spectrum of stars but emission lines characteristic of glowing gas, the revelation was seismic. The nebula was not a star cluster, it was a cloud of hot gas, confirming Laplace's old hypothesis that solar systems could form from collapsing gas clouds. The light itself had become a messenger. In its colors and lines was written the nature of distant matter, its composition, temperature, and even motion. With the advent of the Doppler effect, astronomers could measure the radial velocity of stars. Those moving toward Earth showed a blue shift in their spectra, those receding, a red shift. Space had begun to move, but light carried another, subtler message. It traveled at a finite speed, 300,000 kilometers per second. This meant that every glance skyward was a glimpse into the past. When Herschel said his telescope reached back 2 million years, he wasn't speaking metaphorically. Light became time, and space became memory. The stars were not as they are, but as they were. In this way, cosmology became not only a science of structure, but a chronicle of ancient light. By the late 19th century, the fusion of physics and astronomy, what would soon be called astrophysics, had reshaped our understanding. Yet one riddle remained unchanged and unresolved. Why is the night sky dark? If the universe were infinite and eternal, filled uniformly with stars, then every line of sight should end in a star, and the sky should blaze with light. This paradox, sometimes called Olber's paradox, haunted cosmology. Victorian scientists explained it by invoking a finite universe, where stars did not extend infinitely, and space eventually ran out. But other possibilities, some more radical, lurked beneath the surface. Hierarchical models returned. Scientists such as Fournier Dalbe and Carl Charlier revived the notion of fractal universes, structures in which stars clumped into galaxies, galaxies into clusters, and so on. If the density of matter decreased fast enough at larger scales, the night sky could remain dark, even if the universe were infinite. In such a universe, space wasn't empty. It was textured, recursive, and perpetually unfolding. From deserts and oceans, where light pollution does not dilute the sky's message, the Milky Way arches overhead like a silent script to those who once navigated by its light or prayed beneath its glow. The night sky was not a question, it was an answer. But to the minds awakened by physics and philosophy, it became something else entirely, a boundless riddle. The modern cosmos, just beginning to reveal itself by the end of the 19th century, had grown too vast, too intricate to be reduced to allegory. Stars no longer twinkled in a perfect crystalline dome, they orbited black holes, collided, exploded as supernovae, and whispered their stories across billions of years through the slow, persistent drift of photons. The telescope had become a time machine, the spectroscope a chemical translator, and the sky a record of ancient and future truths. But what if this record, in all its grandeur, was only the surface? Beneath the elegance of law and spectrum lay something stranger still, a universe not merely vast, but recursive, not just old, but entangled with our perception of time itself. In the flicker of a candle, light leaps from the flame and travels outward, unstoppable, weightless, untouchable. It moves across furniture, reflects from bookshelves, glances off the curve of a teacup, and eventually fades into walls or windows. But in space, it does not fade. It stretches. It remembers. Long after its source has changed or died, light carries a ghost image, a final photograph, frozen in flight, frozen in. For centuries, Humanity misunderstood the implications of light's speed. Even as the waves and particles of light were debated, its velocity finite, calculable, and constant remained a footnote rather than a compass. The discovery by Ola Roemer that Jupiter's moons appeared delayed when Earth moved away from them was more than a triumph of measurement. It was a mirror turned on time itself. Once the finite speed of light was accepted, a new, profound realization emerged. To look at the stars was to look back into history. Each twinkle in the night sky was a story from the past, a message delayed by the tyranny of distance. A nearby star might send its greeting from a few years ago. A distant galaxy spoke in million-year-old syllables. The edge of the visible universe offered whispers from near the beginning of time. Space became a layered archive, where depth was synonymous with age. The further out astronomers looked, the younger the universe appeared, not because of evolution, but because of delay. The observable universe, then, was not a structure in space, but a cone in space-time, widening backward, filled with shadows of everything that once was. This changed everything. The Victorian universe, still dominant in public imagination, envisioned the cosmos as a tidy estate, a single galactic mansion set amidst a black, windless sea. It was an elegant model, centralized, comprehensible, divine. But as astrophysics advanced, that mansion began to collapse under its own philosophical scaffolding. Darkness itself became a clue. The absence of light between stars was not just empty space, it was evidence. In an eternal, infinite universe filled with stars, there should be no darkness. Every part of the sky should be saturated with starlight. Yet we have night. This was not merely a poetic paradox, it was a physical one. Solutions emerged. One argued that light from distant stars was absorbed by interstellar dust, but dust, too, would eventually heat up and re-radiate, defeating the argument. Another said that the universe had a finite number of stars, or that it was simply not old enough for their light to have reached us. These solutions leaned on time, not space, as the limiting factor. In essence, the night sky was dark because the universe had a beginning. If light is time's courier, then the cosmos is not a space through which light travels, but a tapestry woven by that journey. Observing a galaxy 10 billion light-years away is not to see it 10 billion kilometers distant, but 10 billion years old. It is to see it not where it is, but where it was. The notion that we are seeing the universe as it truly is collapses under this realization. We are witnesses to a memory, stitched together from radiant fragments. And if light encodes time, what does that say about the thermodynamic arrow, the inexorable drift from order to disorder, from low entropy to high? In the 19th century, thermodynamics emerged as a powerful framework for understanding the physical world. Entropy, once a mathematical abstraction, became a fundamental measure of cosmic direction. The universe is not static. It is a machine that runs down. Stars burn their hydrogen. Galaxies drift apart. Entropy increases, and with each increase, information is lost. Configurations become less reversible, and the clarity of structure gives way to the haze of equilibrium. If time has a direction, it is not just because clocks tick forward, but because entropy dictates an irreversible march toward disorder. This posed a devastating question: is the universe dying? Heat death, the ultimate state in which all usable energy is exhausted, and no work can be performed, emerged as a prediction grounded in thermodynamic law. The stars would fade, the galaxies would dim, and the cosmos would become a thin, cold mist of particles and radiation. Nothing could escape this fate, because physics itself had spoken. Yet even in that bleak prognosis, human thought refused surrender. Hierarchies were imagined nested universes, fractal arrangements of stars and systems, each level containing the seeds of another. Some scientists wondered if our universe was itself the product of a larger system's entropy. the cast-off heat of a higher-order event. In 1952, Walter Baade helped resolve a lingering inconsistency in cosmology. It had appeared that our galaxy was too large compared to others too grand, too exceptional. By differentiating between two types of stars, population 1, young and metal-rich, and population 2, old and sparse, he corrected distance calculations. The Milky Way was no longer bloated in the cosmic census. It had been mismeasured. The stage was reset. Meanwhile, another kind of light cosmic background radiation was theorized. If the universe began in a hot, dense state, there should be a relic glow, cooled by expansion, bathing all of space. It would be ancient, uniform, and isotropic. And though this radiation had not yet been observed, its theoretical fingerprint began to shape cosmological thought. We were now chasing the afterimage of a beginning, not a metaphysical genesis, but a physical explosion, the Big Bang. The term was coined in derision, but it stuck, because it named something tangible, a universe with a past, a trajectory, and a thermodynamic gradient, a universe whose history could be measured, not merely imagined. If darkness at night revealed the universe's youth, and spectral shifts revealed its motion, then entropy revealed its direction. These were not just scientific insights, they were revolutions in ontology. The universe was not a container, it was a process. To measure time is to measure change, and to measure cosmic time is to watch change unfold not in seconds or centuries, but in epochs, the cooling of plasma into atoms, the birth of stars from interstellar clouds, the assembly of galaxies from primordial filaments. Each layer of light is a fossil, and the cosmos is a museum lit by photons that have not yet caught up with the present. But perhaps most haunting is this: the present itself is always slipping. The light we see, even from the moon, is old. The sky above is not the sky now, it is the sky then. The observer stands in a now that is never truly synchronous with the observed. Reality is stitched from delay. If this seems like a metaphysical trap, it is, and yet it is a trap of our own, making a byproduct of insisting that knowledge must mirror simultaneity. The universe does not care for such symmetry. It offers instead a different kind of truth that time and light, entangled, give us not the universe as it is, but as it was, across 1,000 scales and stories. In this way, astronomy became biography of stars, of systems, of space itself. Each photon that reaches Earth is a fragment of a narrative written in distance and decay. It is a messenger from a version of the universe that no longer exists. And what, then, of us? We stand in the middle of this great glowing cone of delayed light. We are the last recipients of stories written billions of years ago, and with our own telescopes, equations, and minds, we write new stories, extrapolations, hypotheses, maps of meaning drawn not from presence but from echo. The universe does not whisper its secrets. It shouts them across the abyss, in wavelengths and spectra, in curvature and cold. But to hear it, one must listen not to the sound, but to the silence between, where time waits in the stillness of old light. A falling apple did more than draw Newton's gaze. It inaugurated a vision of the universe as clockwork, a world where force reigned, vectors directed, and mass obeyed. Gravity, for Newton, was an invisible tug, instantaneous and universal. Every object pulled on every other object, not through ropes or levers, but across the nothingness of space. And yet, that space, absolute, immutable, and eternal, was an assumption. Time, too, was treated as a fixed backdrop, ticking uniformly for all observers. This scaffolding served well for 2 centuries. It let planets be predicted, comets be tracked, and tides be tamed. But it failed to ask a more haunting question: what if the scaffolding itself was dynamic? In the early 20th century, Albert Einstein took this question seriously. He didn't just ask what space and time contained, he asked what they were. and what he discovered shattered the illusion of a passive cosmos. In 1915, Einstein presented the general theory of relativity. At its heart was a radical claim: gravity is not a force, it is geometry. Mass and energy, he said, warp space-time. And space-time tells mass how to move. The apple falls not because the Earth pulls it, but because it follows the straightest path through a curved four-dimensional reality. This path, a geodesic, is not imposed by force, but by shape. To accept this is to abandon intuition. It is to imagine Earth orbiting the Sun not as a rock pulled by tether, but as a marble spiraling along a curved sheet. And this curvature, gentle at planetary scales, becomes extreme near neutron stars, black holes, and the core of collapsing galaxies. Light, too, obeys this curvature. It bends around massive objects, its path deflected by the invisible wells of geometry. This prediction gravitational lensing was confirmed during a solar eclipse in 1919, when starlight grazing the Sun was seen to shift, its apparent position displaced by the Sun's invisible grip on space-time. The universe had become elastic. Space was not a void, but a participant. Time was not universal, but local. Events no longer unfolded simultaneously for all observers. Simultaneity had fractured. This shattered the absolute time of Newton and replaced it with relational time. Clocks on satellites tick differently than those on Earth. Signals from pulsars arrive warped by the gravitational wells they pass through. Even aging becomes relative faster in weaker gravity, slower near massive bodies. These are not metaphors. They are engineering constraints in our GPS systems and scientific lifelines in black hole research. If general relativity reshaped how we understood gravity, it also redefined cosmology. Instead of static, the universe became dynamic. Space could stretch, time could accelerate. Entire volumes of the cosmos could evolve, not in isolation, but as part of a single, mutable continuum. This conceptual leap revived a long-dormant question: had the universe always existed? The mathematics of general relativity suggested otherwise. Solutions to Einstein's equations implied that the universe might be expanding. If so, it must have once been denser, perhaps infinitely so. A beginning loomed, not a mythic origin, but a boundary condition in space-time, a singularity where density, temperature, and curvature reached unimaginable extremes. In 1927, Georges Lemaître, a Belgian priest and physicist, proposed what would become known as the Big Bang. The universe began as a primeval atom, exploding outward in a great unfolding. His model was met with skepticism. A dynamic cosmos clashed with the still cherished image of an eternal one. Yet data began to accumulate. Edwin Hubble, using observations of distant galaxies, showed that their light was redshifted, stretched toward longer wavelengths, as if they were moving away. The more distant the galaxy, the greater its redshift. Space itself was expanding, not the galaxies within it. This wasn't movement through space, it was the growth of space itself. The Doppler effect had matured into cosmological redshift, and the expansion of the universe was no longer hypothetical, it was measurable. Einstein, who had initially introduced a cosmological constant to preserve a static universe, reportedly called its inclusion his greatest blunder. Reality, it turned out, favored expansion. And yet, what was expanding? Not into anything, but within itself. The fabric of space stretched like dough rising in an oven. No edge, no center, no outside. Every point receded from every other. To live in such a universe is to inhabit a paradox. Everything moves apart. Yet no one place is privileged as the point of divergence. This expansion rewrote the meaning of distance. A galaxy a billion light years away is not a billion years old. It is the remnant of what that galaxy once was, its light diluted and delayed. And due to the stretching of space, it may now be far beyond what its original position implies, perhaps unreachable, perhaps already gone. The observable universe, Then is a horizon not a limit of what exists, but of what we can know. Beyond it, light has not yet reached us. Those realms are not inaccessible by geography, but by history. The boundary of the visible is not a wall, but a clock. Cosmic time, now formalized as look-back time, gives us a history in layers. From the cosmic microwave background, a relic glow from when atoms first formed, to the faint blue galaxies at the farthest edge of detection. We see a universe in adolescence, youth, and infancy, and we see it all at once, embedded in space. This time mosaic forces a rethinking of ontology. In daily life, objects coexist: a table, a bird, a voice. But in cosmology, coexistence dissolves. The galaxy we study might no longer exist. Its light is an obituary arriving late. Every astronomical photograph is both presence and absence, both now and then. The observer, once assumed to be detached, becomes central. We do not merely observe the universe, we slice it with our moment. Each redshift, each photon, each measurement is a dialogue between the present and the past. What then is reality? In general relativity, reality is not static. It is foliation, a sequence of spatial slices, each tied to a moment in time, each observer seeing a different cut. There is no single universal now. Each vantage point carries its own temporal frame, its own truth. This is not merely physics. It is philosophy reborn in empirical form. The ancient arguments of Zeno, Plato, and Kant about motion, perception, and causality are no longer abstract. They are measurable in the drift of satellite clocks and the arc of starlight around gravity wells. Einstein's equations, intricate and symmetrical, do not only describe stars and planets, they describe the architecture of causality. What can influence what? What can escape? What remains forever hidden behind horizons? Nowhere is this clearer than in the concept of a black hole. When a massive star collapses, its escape velocity exceeds the speed of light. Nothing, not even photons, can flee. From outside, the star seems to freeze at its event horizon. But inside, space-time continues. The center becomes a singularity, where curvature becomes infinite and our laws of physics unravel. To enter a black hole is to cross a threshold not of space, but of determinism. The known becomes unknowable. The fabric of reality folds inward, and time becomes space, and space becomes time. The metaphors fail because the geometry does not obey human intuition. But the equations persist. And so, we find ourselves at a precipice. The universe is not a static theater in which events unfold. It is the unfolding. Its shape determines its story, and its story, rich in curvature and consequence, invites not just understanding but awe. Yet awe, too, must evolve. No longer the awe of immensity alone, but of structure. Not of size, but of interrelation. Awe, now, belongs to the realization that our universe is a fabric stitched by energy, shaped by mass, curved by presence, and illuminated not by metaphor, but by mathematics. And still, one question remains: if space can stretch and time can bend, what is the ultimate shape of everything? Not in volume or contour, but in causality, in logic, in the possibility of knowing. The next chapter, then, must unfold not just outward, but inward, toward the human mind that maps such things, and the principles that shape its vision of the cosmos. Imagine a speck smaller than a proton, hotter than the core of any star, denser than all matter in the observable universe combined. Now imagine that speck not suspended in space, but being space itself, not in time, but being the origin of time. This is no allegory. It is the leading hypothesis for how our universe began. According to the Big Bang model, the early universe was not a place inside which things happened. It was the happening. A turbulent eruption from a singular point where the known laws of physics, derived from general relativity and quantum mechanics, cease to cohere. Yet this beginning is not the explosion of classical imagination of debris flung outward into emptiness. There was no outside. What expanded was the metric of space itself. Every inch, every atom, every particle of vacuum raced away from every other in a moment of unfathomable inflation. Inflationary cosmology, proposed in the early 1980s by Alan Guth and others, addressed persistent mysteries in the standard Big Bang model. Why is the universe so smooth on large scales, despite being causally disconnected in early epochs? Why is it so flat, neither curling in upon itself nor expanding chaotically? Why do we not observe magnetic monopoles, hypothetical relics predicted by high-energy physics? Inflation answered these with one sweeping gesture, a phase of exponential expansion in the first tiny fraction of a second. Driven by a field called the inflaton, space grew by a factor greater than 1060 in less than 10 to 35 seconds. Quantum fluctuations during this inflationary burst were stretched across cosmic distances, seeding the structure we now observe as galaxies, clusters, and voids. These fluctuations left imprints on the oldest light in the universe, the cosmic microwave background, a faint bath of radiation released when the universe cooled enough for atoms to form and photons to travel freely. First detected in 1965, the CMB became our Rosetta Stone for early cosmology. Its slight temperature variations encode the universe's initial conditions, now mapped with stunning precision by satellites like COBE, WMAP, and Planck. And here, in the afterglow of creation, quantum mechanics whispers across cosmological scales. The uncertainty principle so familiar in particle physics finds its cosmic avatar. Minute energy jitters in the quantum vacuum, once confined to the subatomic world, were amplified by inflation into the architecture of the universe. Galaxies are, in essence, quantum shadows magnified by gravity. But with inflation came a deeper riddle. The inflaton field, like other quantum fields, does not behave identically everywhere. It undergoes fluctuations. In some regions, it decays and reheats space into particles and radiation. In others, it continues to inflate. This leads to eternal inflation, a process in which inflation ends in pockets bubble universes while continuing elsewhere. Each bubble becomes a universe with its own laws, constants, and particles. Thus emerged the concept of the multiverse. Our universe may be one island in an infinite archipelago, not metaphorically, but mathematically. A single field's stochastic decay can yield an ensemble of outcomes, each causally disconnected from the next. Some may be sterile, others, like ours, may birth stars, chemistry, and observers. The anthropic principle, once a fringe idea, is now discussed as a selection effect. We observe this universe because it permits observation, yet many recoil from this vision. It smacks of resignation. It risks replacing explanation with happenstance. If everything exists somewhere, do laws mean anything at all? These are not idle questions. They pierce the boundary between physics and philosophy. The multiverse is not directly observable, at least. Not yet. It cannot be tested in the way traditional theories can. And so, it straddles the uneasy zone between science and metaphysical speculation. But the implications are staggering. The constants of nature, the strength of gravity, the mass of the electron, the cosmological constant may not be fundamental, but environmental. They may vary across the multiverse like humidity varies across Earth. And we, delicate arrangements of carbon and time, may be tuned not by design but by necessity. If gravity were stronger, stars would collapse too quickly. If electromagnetism differed slightly, chemistry would fail. If the vacuum energy were higher, galaxies would never have formed. We teeter on a knife edge, balanced by parameters that, in the multiverse view, are neither rare nor chosen just local. Still, we ask, does a theory that predicts everything explain anything? Quantum cosmology wrestles with this. It seeks a framework in which the universe itself is described by a wave function, a superposition of possible geometries, matter distributions, and histories. In the Hartle-Hawking no-boundary proposal, the universe has no edge in time, just as Earth has no edge in latitude. It begins not with a singularity, but a smooth emergence from a quantum fuzz. In such models, the laws of quantum mechanics apply not just within the universe, but to the universe. This reframes the observer. No longer a passive recipient of cosmic signals, the observer becomes entangled with the cosmos, its history, probabilities, and realities. Measurement collapses wave functions. But when the entire universe is the system, what does it mean to measure who, if anyone, is outside? The Copenhagen interpretation fails here. Everett's many worlds interpretation, where each quantum outcome branches into a parallel reality, resonates more closely. Perhaps each universe in the multiverse is a branch in this cosmic wave tree. Perhaps decoherence, the process by which quantum states lose their interference due to entanglement with the environment, is why we experience only one thread. Yet even this invites further reflection. If reality is fundamentally quantum, is causality itself emergent? Is time a derivative phenomenon? Can the arrow of time, our sense of past to future, be explained by entropy alone? Or must we embed it in the quantum structure of space-time? Cosmology, once the study of stars, now asks these questions. It is no longer content to map galaxies. It must map possibility space. And in doing so, it confronts its own boundaries, not just observational or mathematical, but existential. The limits of what can be known, the nature of explanation, the meaning of a law in a universe that may be but one pixel in a quantum ensemble. Still, the narrative must proceed. The cosmos continues to evolve. Galaxies collide. Stars ignite and die. Black holes consume and evaporate. The expansion accelerates. The fate of the universe is no longer philosophical, it is calculable. And it is to this fate, the slow cooling, the darkening, the potential rebirths or final stillness, that we must now turn. In the distant future, tens of billions of years from now, the night sky will grow darker, not from clouds or cosmic dust, but from the expanding silence of the universe itself. Galaxies that now dazzle the sky will vanish beyond the cosmic horizon, their light stretched into oblivion by the accelerating expansion of space. This is not speculative fancy. It is the cold trajectory traced by current measurements. The culprit is a quiet, pervasive force known as dark energy, first glimpsed at the turn of the 21st century, when supernovae surveys revealed that the universe's expansion is speeding up. What drives this acceleration is unclear: a cosmological constant, a dynamic field, or a modification of gravity itself. But the effect is undeniable. Space is not just stretching, it is racing away from itself. As expansion continues, distant galaxies recede faster than light can reach us. One by one, they vanish not by destruction, but by causal disconnection. Eventually, only the local group of galaxies, gravitationally bound, will remain visible, and even these will merge into a single swollen remnant drifting in isolation. Stars will burn out. The brightest, most massive ones die quickly, in cataclysmic supernovae. The smaller stars, red dwarfs, burn for trillions of years, far longer than the universe has yet existed. But even they will fade. In time, only embers will remain: white dwarfs, neutron stars, and black holes. This is the heat death scenario, a universe approaching thermodynamic equilibrium, where energy differences have smoothed out and no work can be done. A cosmos of stillness. It echoes the second law of thermodynamics: entropy always increases. But entropy is not just a thermal quantity, it is a narrative force. It explains why the past is different from the future, why we remember and do not pre-member, why eggs break but never unbreak. The arrow of time, for all its psychological immediacy, is rooted in a statistical drift toward disorder. Still, even here, surprises persist. Black holes, once thought to be eternal, may not be. Hawking radiation quantum fluctuations near the event horizon suggest they slowly evaporate. over eons. Even these cosmic vaults will vanish, leaving behind nothing but faint photons and gravitational murmurs. Then, perhaps, comes the era of quantum quiet, a universe empty, dark, and cold, but not quite nothing. Virtual particles flicker in the vacuum. Time, if it exists, creeps without witness. The stage remains, but the actors are gone. And yet, physics entertains further possibilities. Some models suggest the expansion will not continue forever. A hypothetical big crunch where expansion halts and reverses into a collapse would reset the cosmos in a fiery implosion, or perhaps a big bounce where contraction rebounds into another big bang, launching a new cycle. More exotic still are cyclic or ekpyrotic cosmologies, where our universe is but one phase in an eternal sequence of expansions and contractions. In these scenarios, the universe renews itself not in a single explosion, but through rhythmic cycles stretching across unimaginable epochs. Such ideas are not merely poetic. They arise from attempts to reconcile general relativity and quantum mechanics, to understand the initial conditions of the cosmos, and to resolve paradoxes like fine-tuning. Time, in these models, is both real and illusory. On one hand, it orders events. On the other, it may be emergent, a product of entanglement, complexity, or our own embedded cognition. Julian Barber argues for a timeless universe, a configuration space of all possible nows, with motion and change as illusions. Lee Smolin counters with a relational time real, evolving, and fundamental. Even space may be emergent from networks of information, spin foams, or quantum entanglement. In this view, space-time is not a container, but a consequence. The universe is not embedded in space, it is space, shaped by its own interactions. And what of life? Some speculate that advanced civilizations might manipulate entropy, extract energy from black hole evaporation, or engineer baby universes via quantum tunneling. These ideas, while remote, raise profound questions. Is the universe hospitable to intelligence merely by accident, or does intelligence play a role in shaping cosmological fate? The participatory anthropic principle, advocated by John Wheeler, posits that observers are not passive recorders of reality, but active participants, that the universe, in some sense, comes into being through observation. In quantum mechanics, observation collapses the wave function. In cosmology, it may do more. But such views border on metaphysics. What remains is a cosmos that, despite its scale, is graspable. A universe that obeys laws, reveals patterns, and yields to human inquiry. And what of our place in it? We are recent arrivals, life forms on a small planet orbiting an ordinary star in an unremarkable galaxy. Yet through reason and observation, we have charted billions of light years, reconstructed billions of years, and begun to model the totality of space-time. From Newton's clockwork to Einstein's curvature, from quantum foam to cosmic acceleration, we have pursued coherence amid chaos. Not all answers are in, and perhaps they never will be, but in questioning, we forge meaning. The boundary of knowledge is not a wall, but a horizon expanding as we move. Each answer begets deeper questions. What set the initial conditions? Why these laws and not others? What is the relationship between consciousness and cosmology? Such questions do not weaken science. They empower it. They transform cosmology from map-making into meaning-making. For the universe is not only vast in size, it is vast in implication. And so, we end not with finality, but with orientation. Not with a closed book, but a compass bearing. We know that light travels for billions of years, that stars are born, die, and seed the cosmos, that galaxies form patterns like filigree across space-time, that the universe had a beginning at least in our coordinates and may have an end, that time is not just a measure but a mystery. We know we are part of it, a transient mode of awareness in a long unfolding, and that, perhaps, is the most profound realization that the universe can know itself through us.
A star burns in the constellation Orion, a red glow pulsing against the black canvas of space. Betelgeuse, a supergiant 600 light-years distant, has captivated human eyes for millennia. Its light, leaving its surface 6 centuries ago, carries secrets of a stellar life nearing its end. Astronomers watch it now, noting flickers and fades, a rhythm that hints at an imminent cataclysm. This star, 15 times the mass of our Sun, has lived a brief, ferocious existence, consuming its fuel in 10 million years, a cosmic sprint compared to our Sun's steady marathon. Its surface, vast enough to swallow Jupiter's orbit, churns with heat and instability, a furnace radiating 100,000 times the Sun's power. In recent years, Betelgeuse has stirred. It dimmed sharply between 2019 and 2020, losing 2/3 of its brightness, an event astronomers called the Great Dimming. Telescopes trained on its surface saw clouds of dust, perhaps ejected during a massive convulsion, obscuring its light. Then it flared again, pulsing brighter, its cycles erratic. These changes, tracked by observatories like the Atacama Large Millimeter Array, reveal a star in turmoil. Its core, fusing heavier elements like carbon and oxygen, approaches a critical threshold. When it reaches iron, fusion will falter, and gravity will seize control, collapsing the core in seconds. Such a collapse could birth a supernova, an explosion so luminous it might rival the moon's glow in Earth's sky, visible day and night. It would outshine Sirius, the brightest star we know, lingering for weeks, 600 light-years away. Betelgeuse poses no threat. Its gamma rays and cosmic radiation will dissipate before reaching us. Yet its proximity, in cosmic terms, makes it a spectacle humanity hasn't witnessed since the supernova of 1604, observed by Johannes Kepler. That event, 6,000 light-years distant, dazzled Europe's skies. Betelgeuse, 10 times closer, promises a brighter show. The star's rotation complicates predictions. Spinning once every 20 years, its surface moves at 18,000 kilometers per hour, far faster than expected for a supergiant. This speed, measured through Doppler shifts blue light from the approaching side, red from the receding, suggests a past upheaval. Some propose Betelgeuse devoured a smaller companion star, its gravity pulling in material that spun it faster. Nitrogen in its atmosphere, a sign of deep mixing, supports this idea. Simulations show a companion spiraling inward, merging in a burst of friction and heat, leaving Betelgeuse altered. This merger theory reshapes our view of the star's mass. If Betelgeuse began as a single star, it might have 10 to 15 solar masses, destined for a supernova and a neutron star remnant. But a merger could push it toward 20 solar masses, where collapse might form a black hole, perhaps without a visible explosion. The star's distance, uncertain by tens of light-years, clouds these calculations. Without precise measurements, its fate remains a gamble neutron star or black hole, supernova or silent vanish. Astronomers trace Betelgeuse's pulses, cycles of brightness spanning 1 year and 6 years, to internal convulsions or a hidden companion. Computer models suggest a star, nicknamed Beetle Buddy, orbiting close enough to tug at Betelgeuse's outer layers. Its gravity could stir the supergiant's surface, amplifying its pulses. Direct evidence awaits the supernova itself, when debris patterns might reveal a companion's influence. Until then, observatories scan for subtle shifts in light, hoping to catch the rhythm of this cosmic dance. Humanity's watch began long ago. Ancient Egyptians saw Betelgeuse as a marker in Orion, guiding their myths. Today, backyard telescopes track its flickers, while global networks of professionals analyze its spectra. The star's youth, 10 million years old, means no rocky planets likely orbit it, their formation outpaced by its rapid burnout. Yet its death could seed the cosmos with elements like oxygen and iron, forging the raw materials of future worlds. As Betelgeuse nears its end, it draws us to the sky, a reminder of stars as engines of creation and destruction. The sky above Orion shifts as Betelgeuse pulses, its red light a beacon across 600 light-years. Its behavior flaring, dimming, spinning defies simple models of stellar death. Astronomers, peering through arrays like the Very Large Telescope, see a star stretched to its limits. Its diameter, nearly 1 billion kilometers, dwarfs our suns. If placed at the sun's center, Betelgeuse's edge would engulf Mars. This scale, measured by interferometry combining light from multiple telescopes, reveals a surface roiled by convection. Giant cells of gas rising and falling, like storms on a distant sea. The Great Dimming of 2019 puzzled observers. Betelgeuse faded to its faintest in a century, sparking talk of an imminent supernova. Data from the Hubble Space Telescope pointed to a massive ejection, a cloud of silicate dust blocking its light. This outburst, tied to a convective surge, hinted at instability deep within. The star's core, now fusing silicon into iron, nears a breaking point. Each fusion stage, hydrogen to helium, helium to carbon, releases less energy, accelerating the countdown. Iron, the final stage, marks the end. Its fusion absorbs energy, starving the core of pressure to resist gravity. A supernova's mechanics unfold in moments. The core, denser than Earth's crust, collapses to the size of a city. Protons and electrons merge into neutrons, releasing a flood of neutrinos, ghostly particles that escape the star, carrying away energy. This implosion rebounds, launching a shockwave that tears through the outer layers. The explosion, brighter than a billion suns, scatters elements forged in the star's heart. Betelgeuse's supernova could peak at a luminosity of 2 times 10 to the 38th watts, 500 billion times the sun's output. For weeks, it might shine as a second sun, visible even at noon. Yet the star's mass holds the key to its fate. At 15 solar masses, it would likely form a neutron star, a remnant 10 kilometers across. Denser than an atomic nucleus, a teaspoon of its material would weigh 1 billion tons. If heavier, near 20 solar masses, the collapse might not stop. Neutrons, crushed beyond endurance, would yield to gravity, forming a black hole. This singularity, warping space itself, could swallow the star's light, leaving no trace. Simulations struggle to pin down Betelgeuse's mass, as its distance 550 to 650 light-years varies in measurements. The star's rapid spin, 5 kilometers per second at its equator, adds another layer. Most supergiants rotate slowly, their expansion diluting angular momentum. Betelgeuse's speed suggests a violent past. A companion star, perhaps half the sun's mass, could have merged with it millions of years ago. As it spiraled inward, friction heated the supergiant's envelope, boosting its rotation. Nitrogen, dredged from the core, now enriches its surface. A chemical scar of this merger. Such events, rare but not impossible, reshape a star's evolution, pushing it toward a heavier, black hole-bound fate. The companion theory extends to Betelgeuse's pulses. Its brightness cycles, 1 year and 6 years long, mirror a heartbeat. Models suggest a low-mass star, Beetle Buddy, orbiting at a distance where its gravity tugs the supergiant's outer layers. This interaction could amplify convection, driving brightness swings. Telescopes like ALMA search for spectral shifts, hints of an unseen partner. If present, its orbit would imprint on the supernova's debris, a final clue to Betelgeuse's story. Without direct detection, the companion remains a hypothesis, testable only when the star explodes. Beyond Betelgeuse, the galaxy teems with stars on similar paths. Rigel, Orion's blue giant, burns hotter but younger, its supernova millennia away. Antares, in Scorpius, mirrors Betelgeuse's red glow, another candidate for a near-future explosion. These stars, born in clusters, forge elements that drift into nebulae, birthing new systems. Betelgeuse's death will enrich its region, its shockwave compressing gas clouds to spark star formation. Iron from its core could one day form the hearts of planets, a cycle spanning billions of years. The James Webb Space Telescope, launched in 2021, peers at Betelgeuse in infrared, piercing its dust veils. Ground-based arrays, like the Square Kilometer Array, map its radio emissions, tracing gas outflows. Amateur astronomers, armed with backyard scopes, log its brightness nightly, their data feeding global databases. This collective watch, blending professional and citizen science, captures a star at its tipping point. The supernova, when it comes, will flood detectors with neutrinos, light, and gravitational waves, a multi-messenger event rewriting stellar physics. The star's distance ensures safety. At 600 light-years, its radiation gamma rays, X-rays will scatter harmlessly. A supernova within 100 light-years could strip Earth's ozone, but Betelgeuse lies far beyond this zone. Its light, though dazzling, will pose no risk, a spectacle for all to witness. Ancient observers, from Babylonians to Polynesians, charted Orion's stars, unaware of their fates. Today, we stand ready, telescopes poised, to capture a moment that may already have happened, its light still racing toward us. Betelgeuse's glow flickers in Orion's shoulder, a star on the edge of oblivion. Its pulses, tracked by astronomers worldwide, hint at a deeper cosmic rhythm. Beyond its surface, the galaxy churns with stellar encounters, some close enough to reshape our solar system's fringes. A star, smaller than the Sun, passed within 110 astronomical units 11 billion kilometers billions of years ago. This flyby, closer than Voyager 1's current distance, stirred the outer solar system, leaving clues in the orbits of distant objects. Trans-Neptunian objects, icy bodies beyond Neptune, hold these secrets. Sedna, a dwarf planet 937 astronomical units from the Sun, follows an elliptical path, its orbit stretched by an ancient tug. Two others, moving retrograde opposite the planet's motion, defy the solar system's order. Over 3,000 simulations, run on supercomputers, trace these anomalies to a stellar flyby. A star, 8/10 the Sun's mass, grazed the Sun's domain, its gravity nudging icy bodies into chaotic paths. This encounter, 4 billion years ago, also explains irregular moons like Saturn's Phoebe, captured from the Kuiper Belt. The Oort cloud, a spherical shell of comets encircling the solar system, felt the star's pull. Stretching a light-year outward, this reservoir of ice responds to passing stars, sending comets inward. Such events, occurring every few 100,000 years, pepper the inner planets with impacts. Earth's craters, like Chicxulub, tied to the dinosaur extinction, may owe their origins to distant stellar nudges. The flyby's legacy lingers, a reminder of the galaxy's crowded highways, where stars cross paths over eons. Closer to home, the Sun drifts through a vast cavity, the local bubble, spanning 1,000 light-years. This region of hot, low-density gas formed 10 million years ago when supernovae erupted nearby. Their shockwaves carved a void, compressing gas at its edges to birth new stars. The Sun, entering this bubble 5 million years ago, now floats near its center, a cosmic coincidence. Telescopes like Rosetta, orbiting 930,000 miles from Earth, map this bubble's contours, revealing an asymmetry hotter and denser above the galactic plane. A tunnel, carved through the bubble's cooler gas, points towards Centaurus, discovered by Rosetta's X-ray scans. This structure links the local bubble to distant regions, perhaps the Gum Nebula or molecular clouds. Astrophysicists propose a network of such tunnels, hot gas channels threading the galaxy's interstellar medium. First theorized in 1974, this idea gains traction as Rosetta's data shows the tunnel's edges, glowing with million-degree plasma. The Sun's passage through this network shapes its environment, influencing star formation around us. Betelgeuse, too, exists within this galactic tapestry. Its supernova, when it arrives, will ripple through the local bubble, its shockwave mingling with ancient remnants. The star's mass loss, already underway, sheds gas that cools into dust, seeding the interstellar medium. Observations from the Very Large Array show these outflows, streams of carbon and oxygen that will outlive the star. This material, forged in Betelgeuse's core, could collapse into new stars, a cycle driven by the galaxy's relentless churn. The star's variability, its 1-year and 6-year cycles, draws scrutiny. Photometric data, collected over decades, shows brightness swings tied to convective cells, bubbles of gas larger than Earth's orbit. A companion star, orbiting at 10 astronomical units, could modulate these cycles, its gravity stirring the supergiant's envelope. Spectral lines, split by Doppler shifts, hint at this partner, but confirmation awaits higher resolution scans. The supernova's ejecta, if asymmetric, might betray this companion's presence, a final signature of their dance. Humanity's gaze extends beyond Betelgeuse to other stellar remnants. T Coronae Borealis, 2,600 light-years away, prepares for a nova, a white dwarf, paired with a red giant, accretes hydrogen until it ignites, flaring 1,500 times brighter every 80 years. Its last eruption, in 1946, followed a predictable pattern, a brightness spike in 2015, a dip in 2023. Astronomers, alerted by amateurs, expect its next flare soon, a fleeting glow visible without telescopes. Unlike Betelgeuse's supernova, T Coronae Borealis's nova spares the star, restarting the cycle. Its white dwarf, Earth-sized but sun-massive, pulls gas from its companion, triggering thermonuclear blasts. These events, observed since 600 BCE, mark the binary's rhythm. Amateurs, scanning the northern crown, may spot the next eruption, their alerts triggering global observatories. The nova's shell, expanding at thousands of kilometers per second, glows briefly, a cosmic firework in the galaxy's vast arena. The galaxy's edges hide stranger forces, micro-quasars, like V4641 Sagittarii, 20,000 light-years away, mimic distant quasars. A black hole, 6 solar masses, devours a 3 solar mass star, launching jets at near-light speeds. These jets, aligned toward Earth, appear to move 9 times faster than light, a relativistic illusion. The Hawk Observatory, in Mexico, detects their gamma rays, photons at 200 tera-electron volts. These energies, once tied to galactic cores, now emerge from our cosmic backyard, rewriting models of cosmic ray acceleration. V4641, Sagittarii's jets pierce the galactic void, their gamma rays a beacon from 20,000 light-years. These microquasars, compact binaries of black holes and stars, challenge assumptions about cosmic radiation. Unlike supermassive black holes and galaxies like Markarian 231, 500 million light-years distant, microquasars operate on human timescales, their jets flaring over days. HAWC's water tanks, nestled beneath a Mexican volcano, capture these photons, revealing energies 10,000 times beyond typical stellar emissions. This discovery ties local systems to galaxy-scale processes, a bridge between the near and far. Betelgeuse, closer at 600 light-years, looms as a counterpoint. Its supernova, unlike a microquasar's jets, will be a singular event. Its core, now fusing silicon, nears collapse. Neutrinos, streaming from this implosion, will reach Earth first, detected by underground observatories like Super Kamiokande. Light will follow, a blaze visible across continents. The explosion's shockwave, traveling at 10% light speed, will carry iron, oxygen, and gold, elements forged in the star's heart. These will drift, perhaps forming nebulae where new stars ignite. The star's rotation, measured by ALMA's sub-millimeter arrays, remains a puzzle. Its 5 km/s spin, faster than most supergiants, suggests a merger. Simulations show a companion star, 1 solar mass, spiraling into Betelgeuse's envelope 2 million years ago. The friction, heating gas to millions of degrees, spun the supergiant faster, mixing nitrogen to its surface. This event, modeled on supercomputers, altered Betelgeuse's path, potentially tipping it toward a black hole. Without the merger, it might have followed a neutron star's fate. The local bubble, enveloping Betelgeuse and the Sun, shapes their stories. Formed by supernovae 14 million years ago, its hot gas 10 times hotter than the Sun's surface expands unevenly. Earocita's X-ray maps show a tunnel toward Centaurus, a conduit of plasma linking bubbles across the galaxy. This network, threaded through cooler gas, channels energy from ancient explosions. The Sun, drifting through this cavity, passes star-forming regions at the bubble's edge, their glow visible in ultraviolet. Stellar flybys, like the one 4 billion years ago, connect to this galactic churn. The rogue star, grazing 110 astronomical units, reshape the Oort cloud. Comets, dislodged by its gravity, still trickle inward, some striking Earth. The flyby's influence extends to Jupiter's irregular moons, captured from the Kuiper belt, simulations, run at institutions like Caltech, model these encounters, showing how a star's passage ripples through a system. Such events, rare but inevitable, underscore the galaxy's dynamic nature. T Coronae Borealis, in the Northern Crown, offers a gentler spectacle. Its white dwarf, accreting hydrogen, nears another nova. The cycle, repeating every 80 years, follows a rhythm: a high state in 2015, a dip in 2023. Amateurs, scanning with 10-inch telescopes, may catch the flare, alerting observatories like Keck. The nova's shell, expanding at 2,000 kilometers per second, will glow for days. A contrast to Betelgeuse's weeks-long supernova. Its binary dance, observed since antiquity, links humanity's past to its present sky. Primordial black holes, relics of the Big Bang, add a darker thread, smaller than atoms but asteroid massive. They race through space at 25,000 kilometers per second, passing through the solar system every decade. They nudge orbits subtly. A flyby near Mars could shift its path by centimeters, measurable by NASA's orbiters. The 1908 Tunguska event, flattening Siberian forests, sparks debate: meteor or micro-black hole hawking radiation. Eroding these holes suggests they've dwindled, but precise tracking of Mars's orbit could confirm their existence. Microquasars like V4641 Sagittarii tie these threads together. Their jets, mimicking quasars, accelerate protons to near-light speeds, flooding the galaxy with cosmic rays. HAWC's detections, paired with radio telescopes, map these jets, showing a black hole orbiting a star every 3 days. This system, in Sagittarius, mirrors processes in distant galaxies, offering a laboratory for astrophysics. Its photons, traveling 20,000 years, reach us now, a signal of the galaxy's violent undercurrents. Betelgeuse's story weaves through this cosmic web. Its pulses, driven by convection or a companion, ripple across its surface. The 6-year cycle, longer than most supergiants, suggests deep structural shifts. Photometry from the American Association of Variable Star Observers tracks these swings, feeding models at institutions like MIT. The star's dust clouds, imaged by the Gemini Observatory, obscure its light, complicating predictions. When it explodes, its light will flood these instruments, a dataset spanning centuries. The galaxy spins, a spiral of 200 billion stars, each a story of birth and death. Betelgeuse, pulsing in Orion, nears its end, its red light a signal across 600 light-years. Its supernova, perhaps a neutron star's birth or a black hole's silent collapse, will mark a moment humanity may witness bare-eyed. The star's rapid spin, nitrogen-rich surface, and erratic pulses tied to a possible merger or companion paint a portrait of chaos. Telescopes, from backyard scopes to the James Webb, stand ready, their data a bridge between ancient light and modern eyes. T Coronae Borealis, 2,600 light-years away, prepares a quieter flare. Its white dwarf, feeding on a red giant, will nova soon, repeating a cycle seen in 1946. Amateurs, scanning the Northern Crown, may spot it first, their alerts triggering a global watch. The nova's glow, lasting days, contrasts Betelgeuse's weeks-long blaze, yet both tie humanity to the sky's rhythms. Their light, delayed by centuries, reminds us we see the past, a cosmic archive unfolding nightly. The local bubble, 1,000 light-years wide, cradles these stars, formed by supernovae 10 million years ago. Its hot gas and Centaurus tunnel reveal a galaxy threaded by plasma channels. The sun, drifting through this cavity, passes star-forming clouds, their light a faint glow in ultraviolet. Rosita's X-ray maps, built from orbits beyond Earth's geocorona, show this bubble's asymmetry, a testament to ancient explosions. Betelgeuse's shockwave, when it comes, will ripple through this space, joining a cycle of creation. Stellar flybys, like the one 4 billion years ago, shape this cycle. A star, grazing 110 astronomical units, stirred Sedna's orbit in Phoebe's path, its gravity a sculptor of chaos. The Oort cloud, nudged by such encounters, sends comets inward, their impacts etched on Earth's surface. Simulations, tracing these paths, show the galaxy's crowded nature, where stars brush past every million years. These events, subtle but profound, link the solar system to its neighbors. Microquasars, like V4641 Sagittarii, add a violent pulse, their jets, firing gamma rays at 200 tera-electron volts, mimic distant quasars. HAWC's detections from Mexican mountaintops reveal a black hole devouring a star, its light a 20,000-year journey. These systems, scattered across the Milky Way, drive cosmic rays, seeding the galaxy with energy. Their processes, scaled down from galactic cores, offer a window into the universe's engines, a parallel to Betelgeuse's explosive fate. Primordial black holes, Big Bang relics, weave a final thread, racing at 25,000 kilometers per second. They may graze the solar system, nudging Mars's orbit by centimeters. The Tunguska blast, a Siberian mystery, hints at their passage, though meteors remain the likely culprit, tracking asteroids with telescopes like pan-stars. Astronomers seek these ghosts, their influence a whisper in orbital data. If real, they tie the solar system to the universe's dawn, a link across 14 billion years. These stories, Betelgeuse's collapse, T Coronae's flare, the local bubbles' tunnels, flybys, microquasars, and black holes converge in the galaxy's dance. Each event, from a star's death to a comet's fall, shapes the cosmos we see. Humanity, watching from a rocky planet, charts this dance with tools and wonder. Babylonians, 6 centuries BCE, saw the same stars, their clay tablets marking orbits. Today, we parse their light with silicon and steel, yet the sky's questions endure. Betelgeuse's light, when it flares, will join this archive, a chapter written in fire.
What is life? Is it something that breathes, that moves, that simply exists? Or is it something far more elusive? If a strange microbe were staring at us from a Martian rock, would we even know it was alive? And if life thrived in the oceans beneath Europa's icy shell, or floated in Titan's methane skies, would we recognize it when we saw it? Close your eyes and imagine a tiny rock lying in the frozen silence of Antarctica, just another stone half buried in the windswept snowdrifts of Allen Hills. But this one came from another world. Roberta Score, a lab manager from NASA's Johnson Space Center, was out there in the white void when she found it. At first glance, it looked like any other meteorite, but when scientists brought it home, examined its chemistry, and matched its fingerprint to the Martian surface, it revealed its true origin, Mars. And inside this unassuming piece of ancient basalt, something even more profound, chain-like microscopic structures uncovered through electron microscopy features that resembled fossilized organisms on Earth. Had we perhaps discovered the first whisper of life beyond Earth, locked in stone and time? This single rock, ALH 84001, launched a storm of debate, speculation, and wonder. Scientists scrutinized every micron, every chemical clue. Were these structures evidence of Martian biology, or just geology playing tricks with our expectations? But the rock posed a deeper question, one still unanswered. If life is out there, would we even recognize it? To search for life in the cosmos, we must first ask what life truly is. How do we define it without knowing what it might look like elsewhere? What are the universal signatures of life, if such signatures even exist? Could life be simple, hidden in dust or ocean spray? Or could it be something far stranger than anything we've imagined? In this journey, we'll explore how scientists define life not just as something that eats or moves or reproduces, but as a self-organizing information-storing system capable of reaction, replication, and adaptation. We'll venture from the chemistry of DNA to the lost seas of early Mars, from the cryogenic lakes of Titan to the boiling vents of Europa's abyss, asking again and again, is this where life begins? In December 1984, a small rock resting on the ice fields of Antarctica was picked up by Roberta Score, a field manager from NASA's Johnson Space Center. To the untrained eye, it was an unremarkable find. But ALH 84001, as it was cataloged, would soon become one of the most controversial meteorites in history. Initially identified as a meteorite, its chemical composition later revealed something far more astonishing. It originated from Mars. This Martian exile had been launched into space millions of years earlier by a powerful impact event and had journeyed silently through the solar system before crashing into Earth and resting undisturbed in the icy plains. After its retrieval, scientists conducted intensive studies, and nearly a decade later, a team led by physicist David S. McKay made a startling announcement. Under electron microscopy, they observed chain-like microstructures embedded within the rock features they argued could not be explained by abiotic chemistry alone. These, they proposed, were fossilized remains of Martian microorganisms. The world took notice. NASA's announcement made global headlines. Even President Bill Clinton addressed the nation, framing the discovery as a potential turning point in human understanding of life in the universe. But as the excitement cooled, scrutiny intensified. Other scientists pointed out that such microstructures could be formed by purely chemical processes without any biological involvement. The claim that ALH 84001 harbored Martian life began to fracture under the weight of peer review and alternative explanations. Yet even amid doubt, ALH 84001 continues to serve as a profound reminder of a deeper question. Even if alien life stood before us, would we be able to recognize it? The challenge of identifying extraterrestrial life begins with the challenge of defining life itself. To date, scientific literature offers over 200 definitions, but most of these can be distilled into a core framework grounded in three essential characteristics. First, life must possess the ability to store information. This means encoding details about its internal state structure and function in a stable medium. Second, life must catalyze chemical reactions. It must interact with and respond to its environment, acquiring energy, building complexity, and adapting to changes. Third, life must be able to replicate, producing copies of itself that preserve its structure and functions across generations. The renowned physicist Erwin Schrödinger was among the first to articulate these principles from a physical perspective. He understood that the transmission and preservation of information lay at the heart of life's persistence. From information comes reaction, and from reaction comes replication. These processes together enable what we observe as living systems that move, metabolize, respond, evolve, and above all endure. A more concise but profound definition was proposed later. Life is that which undergoes Darwinian evolution. It is the capacity for change through selective pressure and inherited variation that allows life to adapt and thrive across a range of conditions. On Earth, we see this manifest in all known biological systems. Our own biochemistry hinges on DNA for information storage, RNA for information transfer, and proteins as functional catalysts. DNA stores our genetic code. RNA interprets that code, and proteins carry out the essential reactions of metabolism and structure building. Importantly, these molecules participate in feedback loops. DNA can instruct the creation of proteins that replicate DNA itself. This elegant cycle is the molecular heart of terrestrial life. But when we seek life beyond Earth, we are faced with the daunting question, must alien life mirror this same molecular choreography? If not, how will we recognize it? Even within Earth's biosphere, we encounter ambiguous cases. Take viruses, for instance. They contain genetic material and reproduce, but only within a host. They catalyze reactions, but only passively. Are they truly alive? Then there is abiogenesis, the emergence of life from non-life. At some point on early Earth, chemistry gave way to biology, yet the boundary between the two is neither sharp nor well understood. It is highly likely that early life lacked the full DNA, RNA, protein triad. One leading hypothesis suggests that RNA alone may have been the first self-replicating molecule, giving rise to the so-called RNA world. Such primitive systems would be almost unrecognizable to us today, and yet they would meet the minimal criteria for life. They would evolve, they would interact, they would replicate. To better understand what extraterrestrial life might look like, we must consider the physical and chemical environments in which life is likely to emerge. Solvents are a critical piece of this puzzle. Life, as we know it, relies on a solvent to host biochemical reactions, dissolve nutrients, and mediate transport. On Earth, that solvent is liquid water. Water has several remarkable properties. It is chemically stable, capable of forming hydrogen bonds, effective at dissolving a wide range of compounds, and maintains its liquid state over a broad temperature range. Early life on Earth almost certainly relied on liquid water, and perhaps more importantly on moderate temperatures that allowed water to remain in its liquid state. Though extremophiles exist, organisms that thrive in boiling vents or acidic lakes, the origins of life likely occurred in more temperate, chemically stable environments. Moreover, early life utilized the same elemental building blocks that persist today: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon, in particular, is a superstar of molecular versatility, capable of forming stable and complex molecular structures essential for information storage and catalysis. The upshot is that early life on Earth, while primitive, was not entirely alien to us. It emerged under familiar conditions using familiar chemistry. Thus, it is reasonable, though not guaranteed, to hypothesize that life elsewhere in the universe may follow similar patterns. This hypothesis brings us back to Mars. Billions of years ago, Mars had liquid water on its surface, a thicker atmosphere, and a temperate climate. If life ever began there, it might have been carbon-based, water-dependent, and similar enough to Earth life for us to detect. And this is what made ALH 84001 so compelling. It could have been a glimpse into an ancient shared biological heritage. However, beyond Mars, the story grows more exotic. The icy moons of the outer solar system offer new and alien laboratories in which life might exist. Europa and Enceladus both harbor subsurface oceans beneath thick crusts of ice. These oceans are kept liquid not by sunlight, but by tidal heating from their host planets. Here in total darkness, life might rely not on photosynthesis, but on chemosynthesis, drawing energy from the heat and chemicals emitted by hydrothermal vents. Could microbial life thrive in these subsurface oceans, feeding on dissolved nutrients? Could evolution produce more complex organisms? Perhaps eyeless creatures navigating by touch and echo, suspended in an alien sea. Titan, Saturn's largest moon, presents an even more bizarre possibility. Its frigid surface is dotted with lakes and rivers, not of water, but of liquid methane and ethane. At 180 degrees Celsius, water is as hard as rock. But methane is fluid and could, in theory, act as a solvent for a radically different form of life. Could chemical reactions proceed in such an environment? Could life emerge with membranes, metabolism, and replication, but without the warm, aqueous chemistry of Earth? The search for life in such places pushes our definitions to their limits, but even more extreme possibilities beckon. Might life exist that is silicon-based instead of carbon-based? Might it use ammonia, sulfuric acid, or even supercritical carbon dioxide as a solvent? Could quantum systems or unknown forms of matter support a form of existence that fulfills the criteria of life without resembling anything we currently understand? These possibilities remain speculative. Our only confirmed example of life is terrestrial. But as we begin to explore these questions, our first step must be disciplined. We must begin with what we know. Thus, in the search for the earliest life in the universe, we ground ourselves in the strictest definition. Life that uses water as a solvent exists within a reasonable thermal range and is based on carbon and its associated biochemistry. This definition serves as a foundation. It is the model by which we design instruments, craft experiments, and interpret data. From Mars rovers to Europa landers, from Titan probes to telescopes peering into exoplanet atmospheres, we begin by searching for the familiar. And with time, if we are fortunate, we may one day uncover the unfamiliar. But even then, we will ask, does it store information? Does it catalyze reactions? Does it replicate? If the answer is yes, we may finally say we are not alone. How to make life from cosmic dust to conscious beings. In the spring of 1952, in a laboratory at the University of Chicago, graduate student Stanley Miller initiated an experiment that would mark a watershed moment in the scientific search for life's origins. Working under the guidance of Nobel laureate Harold Urey Miller, designed a deceptively simple apparatus to simulate the atmospheric conditions of the early Earth. Into a sealed flask, he placed water to represent ancient oceans and filled the remaining volume with a gas mixture composed of methane ammonia and hydrogen molecules presumed abundant on the prebiotic planet. A continuous electrical spark arced through the chamber, standing in for the lightning strikes that would have been common in Earth's volatile primordial skies. At first, nothing seemed to happen, but after a few days, the water took on a faint pink hue. After a week, the mixture had turned a deep crimson. When Miller analyzed the contents using paper chromatography, he discovered something extraordinary. The liquid contained a suite of organic compounds, specifically amino acids, the very building blocks of proteins and by extension of life. Miller's experiment delivered a powerful message to the scientific community under the right conditions. Simple inorganic molecules can spontaneously give rise to the precursors of living systems: glycine, alanine, aspartic acid. These were not mere curiosities. They were biochemical fundamentals synthesized from scratch in a glass vessel with nothing more than water, common gases, and a source of energy. The implication was profound. If the chemistry of life could emerge in a lab, perhaps it had also emerged in the ancient pools of a young Earth. What made the experiment even more compelling was its elemental simplicity. The gases used, methane, ammonia, and hydrogen, are among the most common in the universe, composed of the basic building blocks of matter: carbon, hydrogen, nitrogen, and oxygen. These molecules are widespread throughout planetary atmospheres, comets, and interstellar clouds. That such ordinary constituents could yield such complex outputs hinted at a remarkable possibility. Life might not be a singular fluke of Earth, but a natural consequence of universal chemistry. Subsequent analysis of the original experiment's sealed vials revealed that Miller had synthesized even more amino acids than he initially detected, including some not commonly used in terrestrial biology. This raised another tantalizing prospect. The biochemistry of Earth may represent just one solution among many. Life constrained by evolutionary path dependence had settled on 20 primary amino acids, but chemically the potential permutations are far more diverse. The Miller-Urey experiment illuminated a key step in the transition from chemistry to biology but it was only one piece in a much larger puzzle. To trace the origin of life, we must identify where the right ingredients, environmental conditions, and timescales converge. This raises the central question: where else in the universe could such a recipe be fulfilled? The Earth, of course, is our only confirmed data point. Our planet is awash in liquid water, bathed in sunlight, and shielded by a thick but balanced atmosphere. Critically, Earth orbits within the so-called habitable zone of the Sun, a circumstellar region where temperatures are suitable for liquid water to exist on a planet's surface. Move closer to the star and water vaporizes. Move farther away and it freezes. For life as we know it, liquid water is non-negotiable. Every star possesses its own habitable zone, the location of which depends on the star's mass and luminosity. For smaller stars, the zone is compact and hugs the star tightly. For massive luminous stars, the zone stretches far into space. In our solar system, the habitable zone stretches from just inside the orbit of Venus to just beyond that of Mars. Yet only Earth hosts persistent surface water today. Venus, once perhaps Earth-like, underwent a runaway greenhouse effect. The increasing luminosity of the aging sun triggered the evaporation of its oceans, loading the atmosphere with water vapor and driving up surface temperatures. The result was catastrophic: an atmosphere choked with carbon dioxide and a surface hot enough to melt lead. Mars, conversely, suffered a slower fate. Geological evidence indicates that Mars once had a thicker atmosphere and flowing water rivers, lakes, and perhaps even oceans, but the planet's small size sealed its doom, with a weak gravitational grip and a rapidly cooling core. Mars lost its magnetic field early in its history. Without this shield, the solar wind stripped away its atmosphere, and the water eventually froze or sublimated Mars, dried out and fell silent. These cautionary tales underscore how delicate the balance is. Being in the habitable zone is not sufficient. Planetary mass magnetic fields, geological activity, and atmospheric composition all play decisive roles. Even galaxies have habitable zones. Too close to the galactic center, and radiation from supernovae sterilizes everything. Too far out, and heavy elements become scarce, hindering planet formation. But even in the most promising environments within a star's habitable zone, on a geologically active world, with water, life cannot arise without the essential ingredients, organic molecules. This returns us to the question of where those molecules originate. Earth may have begun with water, but not all of it was available at the surface. Much of the early water became chemically bound in the planet's interior or was lost during its molten phase. One prevailing theory holds that water and organics were delivered via impacts from icy comets and carbonaceous asteroids. These celestial messengers, formed in the cold outer regions of the solar system, retained volatile compounds and organics, which they deposited on young Earth during the so-called late heavy bombardment. This idea gained powerful support in 2014 with Japan's Hayabusa 2 mission to the asteroid Ryugu. The spacecraft retrieved dust samples and returned them to Earth. Laboratory analysis revealed a host of organic molecules, including several amino acids. These compounds had survived for over 45 billion years in deep space, shielded from harsh radiation. Their presence implies that the chemistry necessary for life was seeded across the solar system long before Earth's oceans even formed. Other lines of evidence reach further still. In 2003, astronomers detected glycine, the simplest amino acid in giant molecular clouds. These vast reservoirs of gas and dust are the birthplaces of stars and planetary systems. Spectral signatures of complex organics have been identified not only in our galaxy, but in others, even in the light of distant quasars. These findings suggest that the molecular precursors of life are not just widespread, but ancient. The cosmos was cooking organics long before our sun ever shone. The origin of these molecules, in turn, is rooted in the life cycles of stars. The periodic table is a stellar artifact. In 1957, astrophysicists Margaret and Geoffrey Burbidge, William Fowler and Fred Hoyle published a landmark paper describing stellar nucleosynthesis. Stars through nuclear fusion forge elements from hydrogen. Our sun is currently fusing hydrogen into helium. Larger stars go further, fusing helium into carbon, oxygen, nitrogen, and beyond up to iron. When massive stars reach the end of their lives, they explode as supernovae, scattering their enriched cores into space. These explosions also forge heavier elements like nickel and cobalt. But the heaviest elements, gold, platinum, uranium, require even more extreme conditions. It is now understood that the collision of neutron stars with their immense gravitational and nuclear densities can generate the perfect environment to produce these rare elements. The universe, in other words, must be thoroughly recycled by successive generations of stars before life can begin. The Big Bang produced only hydrogen, helium, and traces of lithium. It was not until the first stars formed hundreds of millions of years later that heavier elements began to appear. Life in any form must therefore wait for at least one generation of stars to live and die. Planets rich in carbon, nitrogen, oxygen, and phosphorus only emerge after stellar alchemy has run its course. And only then, in the presence of water and suitable environmental conditions, can amino acids, sugars, and lipids begin to form. Life as we know it is not only rare in its complexity, it is rare in its preconditions. It depends on billions of years of astrophysical preparation, a precise orchestration of heat chemistry, timing, and stability. It is a story not just of biochemistry, but of cosmochemistry, of stars, planets, comets, clouds, and collisions. The Miller-Urey experiment demonstrated the plausibility of this alchemy under the right conditions, but the cosmic laboratory is vaster and older than any earthbound flask. To find the earliest possible emergence of life, we must therefore look not just to Earth-like planets in habitable zones, but also to the distribution of the raw ingredients, organic compounds, water, and heavy elements. We must track the chemistry of the universe backward through time, through stellar generations, through galactic cycles, all the way to the first molecules that ever formed. And eventually, to reach the ultimate origin, we must peer into the era before the first stars were born, into the dark ages of the universe when only hydrogen and helium drifted silently through the void, awaiting their moment to ignite and begin the long transformation from light to life. The earliest possible life. Let us imagine a future moment when humanity finally cracks one of the greatest mysteries of the cosmos. After decades of relentless investigation, theoretical models, experimental efforts, and technological innovation, the elusive identity of dark matter is revealed, not through myth or metaphor, but through the clean, precise lens of particle physics. A single stable particle, previously unknown, emerges as the solution. It interacts only gravitationally and occasionally through the weak nuclear force. The standard model of physics is updated detectors confirm its presence, and laboratories that once buzzed with dark matter pursuits fall quiet. The intellectual fire dims, proposals dry up, and the world of physics turns its focus elsewhere. But not everyone moves on. A quiet circle of researchers, driven not by consensus but by anomaly, remains unsatisfied. There is still a persistent signal, an excess of gamma-ray radiation flowing from the center of the Milky Way. For decades, it was dismissed as noise or as a byproduct of mundane interactions. But now, with the dark matter particle confirmed, the anomaly lingers unexplained. Driven by curiosity and the allure of unfinished business, these scientists pool what little funding they can, building a high-resolution gamma-ray telescope aimed squarely at the heart of our galaxy. And there it is, the expected glow of dark matter annihilation, predictable, consistent. Except for one detail, the signal is not steady. Subtle, almost imperceptible fluctuations emerge. The signal breathes. Minute changes in intensity repeat with maddening irregularity. The team works tirelessly, formulating and discarding theory after theory. Eventually, the funding expires. Disillusioned, the group disbands. Yet one researcher, a former graduate student, cannot let it go. On a restless night, she reopens the archived data and looks again. A new filter, a new method, a fresh eye, and then something unmistakable. A rhythmic pattern hidden in the noise. Every few seconds, the gamma ray intensity shifts up, then down, precisely like a binary signal. It continues, repeats, pauses, then resumes again after a month. And suddenly she begins to write, marking each increase as a 1, each decrease as a 0. The question is no longer about dark matter alone. It becomes something infinitely greater as the universe speaking. To answer such a question, we must first ask, what is life? What is its minimum requirement, and when could it have first emerged? Traditionally, life is defined as a system that can store information, interact with its environment, and most importantly, replicate itself. These are the foundational pillars of Darwinian evolution. On Earth, this triad is fulfilled by the interplay of DNA, RNA proteins, and the dynamic chemistry of carbon-based molecules bathed in liquid water. But such a framework depends on a specific environment, a rocky planet orbiting a stable star with surface temperatures suitable for liquid water and access to a rich supply of elements like carbon, hydrogen, nitrogen, and phosphorus. When then could such a system first have arisen in the universe? We know that the universe began in a blaze of radiation and plasma nearly 138 billion years ago. For the first several 100,000 years, no atoms could form. The universe was too hot, too dense. Only after roughly 380,000 years did the cosmos cool enough for neutral hydrogen to emerge. But even then, there were no stars, no planets, only a featureless expanse of cooling gas and dark matter. The first star's massive, short-lived beacons, composed only of hydrogen and helium, ignited perhaps 100 million years after the Big Bang. These early stars lived briefly, exploding in titanic supernovae that enriched their surroundings with heavier elements, carbon, oxygen, nitrogen, the chemical seeds of biology. And so began the cosmic cycle of stellar death and rebirth. With each generation, the interstellar medium became more chemically complex. It is only after several rounds of such recycling that enough raw material accumulated to allow for the formation of rocky planets. If the timeline holds, then the earliest plausible moment for Earth-like life to arise, life built on carbon, driven by water, and capable of Darwinian evolution, must have occurred somewhere between 100 and 500 million years after the universe's birth. The Earth itself came far later, forming around 46 billion years ago, which means the first life in the cosmos almost certainly predates our own planet. But this still reflects only the biochemistry that we know. What of the chemistry we have not yet imagined? Astrobiologists have long speculated on alternative biochemistries. Water with its polarity and thermal properties may be ideal for Earth life, but it is not the only conceivable solvent. Methane, ammonia, hydrogen sulfide, and even liquid hydrogen fluoride have been proposed. Phosphorus might be replaced by arsenic. Carbon might yield its role to silicon, which also forms long molecular chains. Each substitution brings constraints but also possibilities. In 2007, physicist Vadim Sidovich showed that dust grains in plasma could, under the right conditions, self-organize into complex spiral structures. These are not living things, but they hint that matter, even in the most minimal and non-biological forms, has an innate capacity for order. Yet even these exotic life forms depend on chemistry, and chemistry requires atoms, which in turn require stars. No matter how alien all forms of life conceived so far must await the forging of elements in stellar furnaces. If we seek to push the origin of life even earlier, we must look beyond conventional matter. Theoretical physicist Frank Drake once speculated that life could form in the interior crust of neutron stars. These objects, the ultra-dense remnants of massive stars, possess unique states of matter, nuclear pasta, that exist nowhere else in the universe. Here, atomic nuclei are crushed into bizarre shapes, held together by the strong nuclear force. In such an environment, structures might self-organize, interact, and replicate, driven by the star's intense heat. It is speculation, yes, but within the bounds of known physics. Others have proposed more abstract entities, magnetic monopoles, strung together by cosmic strings forming networks capable of evolution. Yet the very existence of such particles remains unproven. And crucially, such exotic matter still requires energy and structure, conditions provided only by the emergence of stars. And so we arrive at the most radical possibility: life in the dark sector. Over 95% of the universe's mass energy content lies in the form of dark matter and dark energy entities that do not interact with light and remain for now invisible to our instruments. While dark matter is typically modeled as simple and inert, it is possible that it may host complex interactions of its own. There could be multiple species of dark matter particles governed by dark forces capable of forming dark atoms and dark molecules. If so, then a parallel form of chemistry utterly alien to us may exist in the shadows of the universe. If dark matter possesses structure, interactions, and internal energy, then it might also possess evolution. And if evolution is possible, then so too is life. Such life would not depend on stars. It might draw energy from interactions unknown to us. It might have emerged in the very first moments of the universe, long before the first photon of light escaped into the cosmic microwave background. It might still exist now, floating invisibly between galaxies, brushing past our detectors without ever triggering a signal. And perhaps, just perhaps, it is trying to communicate. Perhaps those gamma-ray signals dismissed as noise were structured emissions from intelligences forged in the dark. But such ideas remain speculative. To find the earliest possible life, we must return to what we can constrain. The universe did not produce the first stars until roughly 100 million years after the Big Bang. Only then could heavy elements begin to form. Only then could planetary systems, rocky surfaces, atmospheres, and oceans emerge. Even under the most generous conditions, life as we know it could not have arisen before this threshold. And even if more exotic forms of life emerged earlier, we may never have the means to detect them. The question then becomes not just when life first arose, but whether we will ever know that it did. Information from those ancient epochs is scarce. Time has stretched and faded the signals. The cosmos has expanded, and with it, the evidence has cooled and dimmed. If a civilization rose and fell billions of years before the Earth formed, leaving behind only faint traces encoded in gamma rays or gravitational waves, would we recognize them? Would we understand? Perhaps life began in the shadows, passed through fire, and emerged, blinking into the light. Or perhaps it danced in the dark, unseen and eternal, whispering across the void. The first life may not have looked like us, thought like us, or even existed in the matter we know, but life in all its possible forms has one thing in common: it leaves patterns. and if we are to find it, we must learn how to read them. Where is everybody? On a warm summer afternoon in 1950, the renowned physicist Enrico Fermi found himself immersed in a seemingly casual lunchtime conversation with colleagues at Los Alamos. The subject, as it often does among those who contemplate the fundamental nature of the universe, had drifted toward the prospect of extraterrestrial life. They speculated freely, throwing around ideas about the abundance of stars, the likelihood of Earth-like planets, the evolution of intelligent beings, and whether any of them might have visited us. The discussion moved on as conversations do, until Fermi, who had been silent for some time, abruptly posed a simple yet disarming question: where is everybody? This inquiry, deceptively innocent in tone, belied its profound implications. It is a question that has since reverberated through the decades as the central premise of what is now called the Fermi paradox, a contradiction between high probability and conspicuous absence. Given the vastness of the cosmos, the abundance of potentially habitable worlds, and the immensity of time available for life to arise, why have we seen no evidence of alien civilizations? The paradox challenges our assumptions about the prevalence of life, the evolution of intelligence, and the nature of cosmic communication. The chain of reasoning begins with Earth itself. Our planet is not special in any fundamental sense. It is a rocky world orbiting a main sequence star, bathing in the warmth of a stable energy source, replete with water, carbon-based molecules, and a relatively benign atmosphere. It possesses a dynamic geology, a magnetic field, and a thin yet protective layer of atmosphere factors that together allowed life to gain a foothold, and through the crucible of evolution eventually produce intelligence. But these features are not unique. In fact, our Milky Way galaxy contains an estimated 100 billion stars, and recent observations suggest that as many as 5 billion of them may host Earth-like planets within their habitable zones regions where temperatures permit liquid water to exist on the surface. And this is merely one galaxy among possibly 2 trillion others within the observable universe. Moreover, the principle of mediocrity in physics, the idea that the Earth does not occupy a privileged position, suggests that the conditions for life, while complex, are not unique to our planet. Nature rarely performs singular acts. If a phenomenon is allowed by the laws of physics, and if there is sufficient time and space for it to occur, then it is almost guaranteed to happen more than once. Life, by this logic, should be common. And given the age of the universe, 8 billion years, there has been ample time for life not only to emerge, but to evolve into intelligent forms, capable of technology and communication. Indeed, life on Earth appeared as soon as conditions allowed. Geological evidence places the first microbial life at roughly 38 billion years ago, shortly after the Earth's surface cooled and oceans formed. The process of abiogenesis, whereby inanimate matter gave rise to self-replicating chemical systems, was not instantaneous, but nor did it require billions of years. Life appears to have arisen with remarkable haste, given the planet's violent infancy. This swiftness implies that once the right ingredients are present, life is not only possible, but perhaps inevitable. If this is true elsewhere, then by now the galaxy should be teeming with civilizations. Many of them would have had hundreds of millions, even billions of years of head start on us. Even at modest technological rates, such civilizations could feasibly colonize an entire galaxy within a few million years, a blink in cosmological terms. With self-replicating probes, interstellar travel becomes not a fantasy, but an engineering problem. Civilizations could communicate across light years using radio or laser signals. Artifacts of their presence, whether intentional or accidental, should be detectable. The solar system ought to be littered with evidence, alien probes, megastructures, chemical anomalies, or encoded transmissions drifting in the radio sky. Yet we find nothing. No signals, no probes, no artifacts, no signs of alien technology past or present, not even biosignatures in the atmospheres of distant exoplanets. This is the silence that Fermi found so perplexing. The sheer absence of evidence is not merely disappointing, it is statistically improbable under the assumption that life is common and intelligence a frequent byproduct. Several explanations have been proposed to resolve this dissonance. The first is perhaps the most sobering, that life itself is extraordinarily rare. The path from chemistry to biology may require a precise sequence of events and environmental parameters, so exacting that even among billions of planets, only a handful, perhaps only one, manage to navigate it successfully. Perhaps the emergence of life demands not only water and organics, but a confluence of tectonic activity, magnetic shielding, climatic stability, and countless other factors still poorly understood. If so, Earth may be a statistical outlier, a cosmic accident. Alternatively, life may be common but intelligence rare. Evolution does not favor complexity unless it provides a survival advantage. Microbial life dominates Earth's history and biomass. Intelligence, on the other hand, has arisen only once in 4 billion years. It is not clear that cognition of our kind is a convergent evolutionary strategy. Perhaps the development of tool-use language, abstract thought, and technological capability is the exception rather than the rule. Countless alien biospheres may thrive beneath alien suns, but their inhabitants may lack the desire or the capacity to contemplate the stars. Yet another possibility is that intelligence often arises but seldom endures. Civilizations may emerge, rise to brilliance, and then collapse. The threats are many. Ecological collapse, nuclear self-destruction, runaway artificial intelligence, pandemics, or perhaps even cosmic events like gamma-ray bursts. Technological sophistication may carry within it the seeds of extinction. If civilizations tend to destroy themselves before achieving interstellar reach, the galaxy may be a vast cemetery of dreams, worlds where intelligence once bloomed but left behind no lasting mark. It is also conceivable that we are simply not looking correctly. The methods we use to search listening for radio signals, scanning for atmospheric anomalies, hunting for Dyson spheres may be inadequate or misguided. Alien civilizations may use modes of communication or technology so advanced or so different from ours that we fail to recognize them. Just as an ant cannot comprehend a quantum computer, we may lack the sensory or intellectual apparatus to detect alien activity. Our assumptions may be anthropocentric, blinding us to more subtle or exotic indicators. Some have proposed that intelligent civilizations actively avoid contact, a concept known as the zoo hypothesis, suggesting that Earth is being deliberately shielded or ignored by a galactic community. Others speculate that we are alone, not because life is rare, but because we are the first cosmic pioneers in a young and expanding universe. If intelligence takes billions of years to emerge, perhaps humanity represents the beginning rather than the middle of a galactic story. Meanwhile, searches continue. SETI, the search for extraterrestrial intelligence, scours the sky for radio signals with artificial fingerprints. Infrared telescopes hunt for signs of waste heat from alien megastructures. Spectroscopic studies of exoplanet atmospheres look for biosignatures, gases like oxygen, methane, or ozone that cannot be explained by geology alone. Missions to Mars, Europa, Enceladus, and Titan seek microbial life beneath the ice in salty plumes or hydrocarbon lakes. Every discovery sharpens our understanding, but the silence remains. Still, the paradox endures. The more we learn about the universe, the more likely it seems that life should exist beyond Earth. Yet, with each failed search, the mystery deepens. Perhaps in time we will find that the cosmos teems with life and that our isolation is only temporary. Or perhaps we will confirm that we are truly alone, an extraordinary exception in an otherwise lifeless void. But if we are alone, then the implications are profound. It would mean that intelligence is not merely rare, it is sacred, that our responsibility as the sole conscious observers of the cosmos is immense. We would be the keepers of memory, the only eyes through which the universe contemplates itself. And if we are not alone, if someday we detect a faint signal, intercept a relic probe, or decode a message carved into the stars, then the paradox will finally yield. We will no longer ask, "Where is everybody?" but instead, what will we say to them? Perhaps one day, far in the future, our descendants will voyage among the stars and uncover the tombs of ancient civilizations, dead worlds, derelict machines, forgotten archives, whispering tales of triumph and tragedy. Perhaps they will discover that we were not the first nor the last to ask the question, that others too once looked to the sky and wondered. That in the dark, somewhere beyond the light of our sun, a monument still waits to be found. A distant Göbekli Tepe of alien origin left behind by minds that once dreamed. And in that discovery, we may find not just answers about others, but something essential about ourselves.